morning everybody, and so today this will be the last few lectures on nanoscale energy transport. So since we do not have too many analytical solutions at large Knudsen numbers, we will take up one or two very simple cases for which we can find the analytical solution, and then I will give a computer assignment. So that will be what you will be working on, even in one dimensions, one dimensional transport of phonons, for example using Boltzmann transport equation, and you can for which we have the analytical solution, and you can compare it with your numerical solution and understand how to solve this kind of type of an equation. See, the Boltzmann transport equation is actually an integral differential equation. So this is not something that you come across in a normal partial differential equation course, and also the fact that it is dependent on so many dimensions. So even in one dimension, so you are not solving only in one dimensional space, so you are also solving in the directional space. So therefore it becomes two dimensional, and therefore even in one physical dimension you have to solve with two dimensions. Therefore that itself is computationally intensive, and when you go to 2D and 3D, it becomes a function of 7 coordinates and so on. So it's a rigorous solution, but at one dimensional level you can try to find numerical solutions, and we also have analytical solutions at steady state. You can try to compare your results. Okay. So that's a that's a good way to probably conclude the discussion on nanoscale energy transport. There are also more advanced concepts pertaining to composites, nano composites and so on, but we will not cover that in this particular course. There are also research going on in for example calculating the thermal conductivity of nano structures. Okay. So as I said, in the case of bulk materials, the thermophysical properties are invariant. Okay. And what is peculiar about the nanostructure is the size dependence of these properties, and therefore we call these as the size effects. So this is a very typical word used at nanoscales to denote the dependence of thermal conductivity and for example electrical conductivity, if you take electron charge transport. So all these are function of the thickness of the material that you are considering. Okay. And you can also show that in the limiting case where you have very small Knudsen numbers, so these approach your bulk values. Okay. So when we are talking about nanoscale heat transport or any energy transport, so you generally refer to what is called the size effects. Okay. And let us study one such size effect. We can first start with for example the electron transport. Okay. And that means the flux of the charge, okay, a flux of current. So this is your current flux which gives you the electrical conductivity, and therefore we can first understand the size effect with respect to electrical conductivity, and we will see analogous to that how the thermal conductivity also exhibits size effects. Okay. So to do this, now we are therefore talking about real nanoscale transport. Okay. So I mean, although we were discussing many things about nanoscale right from the beginning, the real nanoscale transport starts here. Okay. So all this till now is to put the perspective on different kinds of subjects such as statistical thermodynamics, quantum mechanics. All these are the fundamental building blocks, and we finally showed that for transport process the Boltzmann transport equation is the fundamental equation, and from which we can derive all the classical constitutive relations. So these were not really nanoscale in that sense. So the real nanoscale transport we will be dealing with now in the next 1, 2 or 3 classes. So, to do this again, let us go back to the way we were deriving our continuum equations. So, in that case we assumed a perturbation function, distribution function from the, which is the difference between the non-equilibrium and the equilibrium distributions. And if you substituted this in terms of G and F equilibrium in the Boltzmann transport equation, so you are having terms which involved G and F equilibrium. So, you had dG by dt, dF equilibrium by dt, plus you also had the gradient with respect to position for both G and F equilibrium, as well as you had the gradient with respect to the momentum space for both of them. And then finally, on this side you had G by tau, scattering term. Okay. The scattering term is approximated by means of the BGK or relaxation time approximation. Okay. So, this is your Boltzmann transport equation. I think all of you should know this by heart, and therefore should be able to write this at any point of time, you know. So, we also made several assumptions in deriving the continuum equations. As I said, that if you look at the order of say dG by dt and dF equilibrium by dt, so in comparison to the scattering term on the right hand side, so these are much smaller, correct, or in other words we said the physical time scales are much greater than your relaxation time scales. Okay. So, therefore, we can also call this in a sense that we are looking at more like a steady state process. We are not bothered about the variation of this distribution over time. Therefore, we neglected the time variation, and we also invoked the assumption that your G should be smaller compared to your F equilibrium, and also the respective gradients of G should be smaller than the counterparts for F equilibrium. So, similarly with the gradient in the momentum space. So, invoking all this, therefore, we wrote your F in terms of F equilibrium minus tau into V dot del R F equilibrium plus F by m equilibrium, right. So, this was the underlying transformation of BTE. Okay. The actual BTE is quite complex. From there we put all these assumptions and then we converted this to this form, which we used to derive all the continuum equations. Okay. But however, now when we are dealing with nanoscale transport, so we are talking about, so in the present case we want to study transport in nanostructures, right. So, in that case we cannot make all these assumptions. Of course, we have to make certain assumptions to solve them for the nanoscale problem as well, but we cannot make these kind of assumptions. So, what are the assumptions suitable for this problem? So, one is we can still make the assumption with respect to the time scales, because we can say that although your Knudsen numbers are high, we are looking at problems where the physical times are greater than the relaxation time. Okay. That means we are not looking at femtosecond or picosecond laser irradiation kind of processes here. Okay. We are looking at clearly size effects, okay, size effects coming from reducing the size of the structure, okay, and not due to disparity in the time scales. Okay. So, therefore, still we can make the first assumption that dg by dt, df equilibrium by dt, these are much smaller than the collision term on the right hand side, because this is still valid. So, this is one important assumption. Okay. So, what is the other assumption that we can make? So, if you look at the term f by m del v g, okay. So, this is the variation, or this is the gradient of the perturbed function in the momentum space. We can say that this is also small compared to the corresponding change in respect to f equilibrium. Okay. So, if you make these two assumptions, so the Bt can be rewritten in Cartesian coordinates, two dimensional Cartesian coordinates. So, we neglect the unsteady terms. So, we have only the advection terms both in the physical space and the momentum space. So, the first term we have v dot del r f naught. If you expand this, we have Vx df equilibrium dx plus Vy df equilibrium by dy, right. And similarly for g, we have Vx dg by dx plus Vy dg by dy, and the other term which is important is df equilibrium by Vx plus Fy by m df equilibrium by dVy. This is equal to minus g by tau. Okay. So, in other words, by invoking the second assumption here, we also say that the whatever deviation function or perturbation function could be quite large in the physical space, okay, because this is a nanoscale phenomenon, you know. So, when you are talking about very high Knudsen numbers, your non-equilibrium function is supposed to deviate quite a bit from your equilibrium function, but this effect comes only with respect to the physical coordinate and not in the momentum space. So, this is therefore a very important assumption. Okay. So, with that assumption, we reduce the dimensions, number of dimensions for g. Okay. So, g therefore is only a function of x and y, whereas f equilibrium is a function of x, y, Vx and Vy. Okay. So, this is your starting point, and let us now consider two kinds of transport. Okay. So, one is you can talk about transport which is parallel to thin films. Okay. Thin films are the nanoscale nanostructures. So, you can talk about a nanostructure like this. So, you have a separation. So, this is your film. The film is thick with units of d, right. So, this is your thickness of the film here. So, it could be of the order of few nanometers, for example, and your coordinate system is attached to the bottom plane. Okay. And you have your momentum space which is Vx Vy, okay, and this is your V vector which makes an angle, let us say theta with the vertical. I mean this is your convenience. If you choose theta here, you can choose the projection of this onto this plane and make an angle phi with the horizontal. Okay. So, it is up to you. In the other case, we chose theta as the angle with the horizontal and then the projection onto the vertical plane, making an angle phi with the vertical line. Now, we are just picking this for convenience. You can also do the other way. Okay. So, now we are talking about a temperature gradient which is not in the vertical direction, but in the horizontal direction. Okay. So, so in this case you have a temperature gradient, or you can have gradient of the Fermi energy level, okay, and you can have a corresponding electric field, right. So, in this case therefore, you maintain a temperature gradient or a gradient in the Fermi level such that the electrons move along the x direction. So, this is a case where your transport is happening parallel to the films, right. So, your film is actually like this, you are confining the film by a dimension d, okay, but the transport is happening along the film. So, the other case where you study your heat transport and all, that is one plate, the bottom side is at one temperature, the top side is another temperature. So, in that case the transport is happening perpendicular to the film. Okay. So, but this is one of the simplest cases you can start with, transport parallel to the thin films. So, in that case, so now let us draw the momentum space separately. So, you have Vx, Vy, Vz, this is your momentum vector and this is your polar angle theta. Now, polar angle we are defining as angle with respect to the vertical coordinate Vy, and the projection of this onto the bottom plane, the Vx xz plane. Okay. So, that will make an angle phi, the azimuthal angle with respect to the x coordinate, Vx coordinate, right. And therefore, now let us look at the terms dF equilibrium by dy. Now, with respect to F equilibrium, now F equilibrium is a function of your x, y, Vx, Vy according to the equation that we have written here. Yeah. So, now in the case where you have transport parallel to the thin film, what will be the most important function? So, F equilibrium variation in the x direction or y direction? In the x direction, because we have transport in that direction. Okay. So, therefore, now when you talk about dEf by dEf equilibrium by dy, so we can actually assume this is smaller than the corresponding deviation function gradient in the same direction. Okay. So, you have very strong gradients F equilibrium varying with x because of either the temperature dependence or because of the Fermi level dependence on x. Okay. So, however, if you look at the variation of g, okay, so in this case g will be a very strong function of y. Okay. So, therefore, in comparison with dg by dy, we can neglect dF equilibrium by dy. On the other hand, if you are looking at dEf equilibrium by dx, so this will be quite strong compared to dg by dx. Okay. So, therefore, now these are again we have made already couple of assumptions here 1, 2 and brought to this form. Now, for the case of transport parallel to the films, we make assumption number 3 and 4. Okay. So, depending on the direction of the transport, you can say what will be the order of magnitude of the derivative F equilibrium. In the x direction it will be very important, significant, whereas in the y direction it will be non-significant. So, therefore, when you write down, let us say this is your equation number 1 and reduced for the case of transport parallel to the film. Can all of you write that down? So, we have df equilibrium or dx very dominant, the second term will be less significant, the third term also will be less significant. Okay. And then we have the fifth and sixth terms. Okay. Out of these two again, when you talk about df equilibrium by dvx, df equilibrium by dvy, which will be more significant? So, we have transport along the x. So, therefore, the external force which will be acting, the electric field or whatever, will be acting in that direction. Okay. So, once again we can ignore df equilibrium by dy in comparison to dvy in comparison to df equilibrium by dvx. So, with all of these assumptions for this case, the Bt will reduce to okay. So, therefore, it depends on the scenario. If you are now looking at the other case, transport perpendicular to the film, so if you maintain therefore a temperature gradient or maintain an electric field in this vertical direction. Okay. In that case, how will you reduce this equation? So, when you talk about df equilibrium, so in which direction will be the gradient? In y direction. So, this will be greater corresponding to dg by dx dy, sorry, right. And similarly, if you are talking about df equilibrium by dx, this will be much smaller in comparison to dg by dx. Okay. And similarly, df equilibrium by dvy will be larger compared to corresponding derivative here. Therefore, for this case you get Vy df equilibrium by dy plus let me just make sure I put the right terms here. Okay. Yeah, so this should be Vx, right. So, this should be Vx dg by dx plus I have Fy by m dF equilibrium by dVy should be equal to minus g by tau. Okay. So, I think this should be fine right now, and what we will do first, let us take the first case, the phonon transport or electron transport parallel to the thin films. So, we will take the case 1, transport parallel to thin films, and can you try to solve, I mean what I can give you as a hint now, take the equation number, let us call this as number 2. So, we have dF equilibrium by dx, we have dg by dy, we have dF equilibrium by dvx. So, now let us group these terms. So, on one side, left side we will group the terms with respect to g, on the right hand side we will group the terms with respect to F equilibrium. Okay. Can all of you do that? So, you group that, okay, and write the right hand side terms which are functions of x, for example, right. So, dF equilibrium by dx, we have dF equilibrium by dvx. So, you can write these as some function of x and then try to get the solution for that particular differential equation. Okay. Just attempt it. So, write one side function of y, the other side function of x, and whatever we have dF equilibrium by dvx, dF equilibrium by dx. So, these are just some function of x, you group all of them as one single function of x and then you try to solve the ODE with respect to y. Okay. So, I hope you could get to this point now, right. So, I am writing on one side the function of y, g is a function of y, and the other side f equilibrium as a function of x. So, all of these on the right hand side together we have one function of x. The reason why we are doing this, in fact, is that now when you take thin films and parallel to that, it is not very obvious whether there will be size effects in this case, right, because you have a confinement in the direction which is perpendicular to the transport. So, you might wonder, if I have a transport in this way, how is this confinement going to bring size effect? Okay. But what is happening in the nano scale is that we are talking about now scattering of phonons or electrons. So, not only electron scattering, but electron boundary scattering is happening. So, this is going to bring about a distortion of the equilibrium non-equilibrium function quite substantially, even when you have transport along the plane, along the film. Okay. The distortion can happen in the perpendicular direction because of this scattering mechanism. Okay. That is why we say that dg by dy is still strong here. Okay. So, your df equilibrium does not change with respect to y. However, your dg by dy we cannot say that, because dg by dy is the reason why we are getting a size effect for this case. Okay. Now, whereas if you look at the transport perpendicular, so there is a small correction that you have to make. So, in the transport perpendicular it is very clear, if you have a temperature gradient in this direction, okay, and you have a confinement in that direction. So, your f equilibrium is going to vary in that direction, and so is your perturbation function. The perturbation function is also very strongly dependent in that direction, not dx. So, please correct that. So, therefore, we do not have dg by dx term here, it will be dg vy dg by dy. So, what should be the ideal case, the way I have written here. So, this should be large, okay, and you can say that, okay. So, this is small and you have dg by dx approximately 0, because in this case the distortion or perturbation cannot happen along x for a case where you have transport perpendicular to the plane. I hope you are able to understand the point. So, when we now do the solution, you will be able to get this fact, but what you have to understand right now is, when we start the problem, where are the nanoscale effects coming from? Okay. So, when you talk about transport parallel to the thin film, so in this case the distortion function still has to vary along y. Okay. So, that is what is bringing the size effect. When you are talking about transport perpendicular to the film, so already the confinement is in the y direction, the transport is also in the y direction. So, distortion function will be varying along the y direction. So, there is no variation of distortion function along x. So, in that case your dg by dx will be 0, you understand. Okay. But still, when you are talking about transport, the f equilibrium will depend on the direction of the transport, but not the perturbation function. Okay. So, in the case of transport perpendicular to the films, so you please correct it, it should be Vy df equilibrium by dy plus Vy dg by dy. So, both the distortion function and f equilibrium will vary along y, whereas in the transport parallel to the films, your f equilibrium varying along x, distortion function varying along y, but without that variation of distortion function along y, there will be no size effects, right. So, that is the one which is causing size effects even when you have transport parallel to the films, okay, and we will see how it is happening, that is because of the boundary scattering, right. So, now when you therefore write this equation for thin films, transport parallel to the films, we are grouping this all the y terms on the left hand side, all the x terms, because what we are more interested is to find the solution of g as a function of y, and this is what contains the size effect information in it. Okay. So, therefore, we for the sake of solution we will just combine the terms with respect to x as one function of x. Okay. For solution with respect to y, this is not required, that can be just added as it is in the end. So, we are more interested in seeking a solution with respect to y, and especially for g as a function of y. Okay. And therefore, when you solve that, so can you solve this particular ODE now? So, we have this is equal to minus S naught of x. So, this is your ODE where you have a non homogeneous term, right. So, there will be a complementary function, there will be a particular integral, the complementary function will be the solution to the homogeneous differential equation. So, what will be that function? So, that will be tau v cos theta into dg by dy plus g equal to 0. This will be the solution to the homogeneous ODE. The solution comes out to be, can all of you please quickly work out and tell me, g as a function of y. So, we can say c exponential minus y by tau v cos theta. So, this is where the actual size effect is coming from. So, you are confining your y direction. Okay. So, you are confining this with a few nanometers. So, this is where the distortion of g is happening along y, and this is going to bring in the size effect for electrical conductivity or thermal conductivity. So, therefore, now if you add also the full solution will be complementary function plus a particular integral now is a function of x, does not depend on y. So, that can be just simply added on to this. So, therefore, you will get the final solution as g of y plus S naught will be equal to c exponential minus y by tau v cos theta. So, you keep this solution right now, and meanwhile, we will find out the expansion for this S naught. Now, we know already that S naught term is basically this, you have df equilibrium by dvx, we have df equilibrium by dx. Just like we did it yesterday's class, we can expand now df equilibrium by dx as df equilibrium by def or dt. So, in this case, let us say you are considering only transport of electron flux, current flux. Okay. So, therefore, this is the dependency of Fermi level on position. So, we can write this as df equilibrium by def into def by dx. Similarly, if you are talking about df equilibrium by dvx, it is a function through E, df equilibrium by dE into dE by dvx, because of the dispersion curves. Dispersion curves give you relation between energy and the momentum. Okay. So, the same way that we did yesterday, right. So, if you do that, the expression for S naught of x will be minus, and you substitute for the force, Lorentz force, okay, charge times the electric field. Okay, it comes out to be minus E times tau Vx df equilibrium by dE into Ex plus 1 by E def by dx. Please check this with yesterday's expansion. We also use the fact that your dF equilibrium by dEf is equal to minus dF equilibrium by dE, right. I asked you to check that. Did you check that? Take the derivative of the Fermi Dirac distribution function with respect to EF, with respect to U, and check. So, they will be same in magnitude, opposite, minus. Did anybody check that? Okay, so you are convinced. Okay. So, all of you could reach to this point, right. So, you have a solution with respect g of y plus s naught is a function of s x, and solution for s naught is already known, right. It is a function of the F equilibrium. Okay. Now here is where we try to understand what is happening to the scattering of electrons. Okay. So, now when you talk about whether it is transport parallel or perpendicular, inevitably you should talk about scattering of electrons at the boundaries, because this is where the confinement effect makes a difference. If there was no confinement, the scattering from the boundaries will be very negligible. Electron scattering will be more predominant over electron boundary scattering. But now when you are talking about a confinement that you bring in, does not matter whether you have transport this way or this way, now you are going to have electrons which come, because as you see from the solution to the BTE, the electrons can travel in a spherical coordinate system, right. So, it need not travel only vertically up or horizontal. So, it can travel in a sphere encompassing all directions of a sphere. So, that can come in any direction. So, electron which is coming like this will hit the boundary and it will change the direction. Okay. So, similarly, the electrons which come to the bottom boundary will hit and they change direction. So, therefore, this process of electron boundary scattering is the one which is causing the gradient of the perturbation function along y. Okay. So, even for transports parallel to the planes. So, if you for example, therefore, look at the scattering mechanism from the bottom boundary. Okay. So, we have assumed the coordinates starting from the bottom wall, and we have the scattering of electrons from the top surface. So, when with respect to the coordinate system that we have taken, for we have Vx, Vy, okay. So, you have V vector. So, we have taken theta with respect to the vertical, right. So, therefore, what angles of theta does this scattering from the bottom correspond to? Theta going from so you can so when you are talking about variation of theta, so theta 0 starts from here, okay, and then you are talking about 0 to pi by 2 and then pi by 2 to pi. So, when you are talking about therefore scattering upwards direction, so what is the variation of theta? 0 to pi by 2, right. And what about the downward scattering? Pi by 2 to, is that clear? So, this corresponds to the scattering in all these directions. This is your upward direction, where theta can vary from 0 to pi by 2, and now if you talk about scattering in this direction, downward direction, your theta can vary from pi by 2 to pi, okay, and the other half is coming because of rotating your phi, okay. So now you are talking about a sphere, so your theta varying from 0 to pi and phi varying from 0 to 2 pi. So you first sweep a semicircle, right, and then you rotate it about the vertical axis, or yeah, correct. So that will bring a full sphere, okay. So therefore we have this direction cosines here. So in this case your direction cosines will be positive cos theta, okay, and in this case it will be negative, right. So we will call this part which is scattered from, which is moving towards the positive, in the positive direction cosine space, as G plus, and the solution which is moving in the negative direction cosine space as G minus. I hope all of you are following this. So we have this G as a function of not only y, in fact it is a function of cos theta as well, okay. So and therefore we have scattering of G going in all directions, even for a one dimensional problem. So we are segregating, we are breaking this into the ones which are going up, scattering and going up, the others which are scattering and going down. We call this as G plus and G minus. So the same solution therefore can be written as, you can say that G plus will depend on y and the positive direction cosine space can be simply S naught exponential, okay, so I have to do one more step here. So the other thing is we have to apply the boundary conditions in order to calculate the constants. So now we will have two constants for this case, one for G plus there will be a constant, the other G minus will have another constant, you understand. So therefore we have two constants, we have to find this by the corresponding boundary conditions. So we have to understand what is the characteristic of the scattering at the boundary, what type of scattering it is. So there are two extreme possibilities. So one is called diffuse scattering, the scenario that I have depicted here, okay. So an electron can come in a direction, downward direction like this, and the surface can be so rough that it scatters in all the directions from the boundary, okay. So this is called diffuse scattering. So in the diffuse scattering you have a uniformity of the emerging distribution over the entire directional space. All of these are uniform, equal, whereas the other extreme is called specular scattering. You have a perfect mirror image, you have like a polished mirror, so it comes in a particular direction, it reflects like a mirror image in a direction which is making theta to the vertical, okay. So we will look at these two boundary conditions in detail in the next class. Based on that we will calculate these constants, find the solution, and we have still not got the final solution. The solution is only for G. Now we have to use this to calculate the current flux, the way we did the yesterday's class, okay. Only difference is yesterday we were doing it for continuum case and now we are going to do for nanoscale case. So we will stop here.